Okay, on the previous two workshops I've built a model of the economy using the unique feature of Minsky, which is its godly tables. Now I want to show building a model in Minsky using features it has in common with all other system dynamics programs, which is the use of a flowchart of some description to model dynamic processes. And Minsky takes a rather different approach to most of the other programs by putting all the equations on screen. Now the model I'm going to take a look at was built by Richard Goodwin back in the 60s. To my way of thinking, Richard Goodwin is one of the most important and neglected figures in economics. A brilliant mathematician, a brilliant feeling for most of capitalism, except for the financial sector. But unfortunately, the way he wrote wasn't exactly easy to understand. So the model he published in '67 was a model built largely as an analogy to predator-prey models in biology, which create cycles of predator and prey, as I explain in my book, The New Economics and Manifesto, and I might also explain here if that helps. But trying to read Goodwin was rather hard. In fact, when I first tried to read it, I understood it, but I really couldn't. It wasn't something that I felt that I could easily build on. And then I read John Blatt's explanation, as I say later in this workshop. Blatt does a brilliant job of explaining this model, much better than Goodwin did himself, though of course it was Goodwin who came up with the idea. So I'm going to build the model as a flowchart, not following the logic that is shown in this paper, but doing it from capital to output and labour, to wage determination, back to the rate of profit, and then back to investment and capital. But I'll later show how it can actually be derived directly from macroeconomic definitions, which is similar to what Goodwin did here, but rather less obscure. So let's start from building it in Minsky, which here I'm using Ravel, as I explained. We're still porting Minsky itself to JavaScript. I would like to use the latest version, but I'll show you why I'm not doing it actually. This is the sort of thing, again, we address with bug fixing. And I think you can tell straight away, even though it might look slightly better, hey, those characters are really small. And the reason is that Minsky, with the JavaScript front end, is not yet getting the signal from Windows to rescale everything. So Ravel here is scaled to 250% relative to the native resolution of this screen I'm working on, which is a 4K screen with 4,000 pixels horizontally and 2,000 vertically. Minsky is just going at 100%, and I can actually, if I put something on the canvas, let's just put a switch on the canvas there, then I can zoom in and see it at a larger scale, but the menu items are still pretty damn small, so I'm not about to try to use that to teach here, so I'm still using the more old-fashioned TCL/TK front end of Ravel to put this model together. So we're going to start from investment, which is this Goodwin's model is an investment-driven model. I've seen a lot of post-Keynesians unfortunately comment and say, well, it's not really a demand-driven model, therefore how can it be Keynesian? They call it a supply-side model. Investment is part of aggregate demand, and the most volatile part of aggregate demand, before we look at the financial sector, which we'll do in the next model. So it's a demand-driven model. Well, let's just get to that point, and I'll generalize that, particularly when I bring in the modeling Minsky on top of Goodwin's foundation. So I'm going to have I, capital I for investment, and I can just type capital I as a text input, and then Minsky pops up a menu item saying, well, what is I? And I'm going to say it's gross, it's net investment after depreciation of capital stock. So there's my net investment, and it's a variable, so I'm not going to give any other definitions to it yet. I can do that later. So there's investment. This is zooming in using the scroll key to do that. So we have investment. Now investment is equal to gross investment minus depreciation. So I'm going to use I underscore G for gross investment there. Again, I haven't defined that yet. Put it on the screen. So what I now need to have is minus depreciation. So I type a minus. Because you can type minus 10 as a constant in Minsky, we don't automatically put a minus key on the keyboard. So if I could be typing -10 here, for example, but if I just type the minus key and press the enter, then I get the minus block. So now I'm going to have depreciation over here. Now, to have depreciation, I have to have capital. Capital is the integral of investment, so I need to bring an integral block here, and that's where Minsky now coincides with the, my wipe up in the video there, I'll just pop that out, take a look at that later. Minsky uses a integral block to do what you see other programmers do with bathtubs and stocks and flows defined in the in a more system dynamic sense. So when you click on the integral DT sign there, you get this little object coming down. You can then edit that. The default name is INT1. I'll just use K for capital there, and now I've got capital at least entered onto the canvas, and now what I want to have is that capital is the integral of investment. So hang on a second. Okay, let's keep going. So I've now got investment, I now need to have depreciation. So if oh, by the way, notice that's a square cursor, which is what you use for moving objects around. Sometimes Minsky gets locked on that, so if you just press the shift key, it'll disappear and go back to the standard canvas. Now I want to take a copy of K, just K on its own, because depreciation is going to be some constant times the existing capital stock. So I now want to type a constant for depreciation, and I'm going to type delta subscript K for using delta to mean change, the Greek letter for D, and K to show talking about change in the capital stock. And this is now going to be a parameter, and the usual rate of depreciation that I tend to use in terms of looking at economic data is about a 6% per annum rate of depreciation, but you can make it as large as 20%, as low as 0, and put in a 1% step size. So now if I have capital multiplied by the actual existing capital stock and subtract that from gross investment, I now get net investment, and now we're getting closer to a overall model, but I now need to define an initial level of capital stock. So just for the sake of it, I'm going to say K_0 is my initial level of capital. I'll make that a parameter for the model, give it a value of 300, say maximum of 600, minimum of 100, step size of 10, so I can vary these things if I need to vary them later. And you attach that to the bottom of the input there, and that's saying the initial value for capital. Now to show what's being defined in terms of equations by Minsky as we're building that, those are the set of the equations. So I have a gross investment currently 0, initial capital 300, rate of depreciation 0.06, net investment is gross investment minus depreciation, initial value of capital is 0, and the rate of change of capital is equal to investment. So that's what Minsky is doing in the background, is building the equations for you, and if you wish to, you can output those equations by exporting the canvas. This is a bit clumsy at the moment. We might improve this in later versions, but you've got 5 ways you can output a model: as an SVG file, which is a vector graphics file that you can put into programs like PowerPoint, Word, and so on to document a model; as a PDF, PostScript, which is the sort of online version of PDF, if you like; a bitmap file, PNG; an encapsulated meta file, again another version of PostScript; LaTeX. Now that's, I'll just actually do that just to indicate what's going on here. So I've actually called this Goodwin 01. Then that will save a file called Goodwin A1.tex, and if I bring up my file manager and go and take a look at that file, let's just go and right click and go to the file location, then that is a text file which you can load into a text into a LaTeX editor. But you can also, if you have Word and you're using MathType, which I do for documentation, you can just cut and paste elements of that into MathType and then document the model as you build it. So I might actually just indicate what that looks like. If I take a copy of that and bring up, let's bring up MathType directly. tick, tick, tick. And if I have the options set properly in terms of preferences, in terms of cut and paste, so that I cut and paste from latex, then if I just type Control V here, and now I've got fun and games with Windows, pardon me. Notice I have a little application called Unfuck. Thing goes wrong with Windows copying and pasting. So now if I go back and take a copy of that text and paste over here, I get the equation shown as you'd want to see it when you're formatting an equation for publication purposes. So Minsky is designed to help you out with getting publications out of the models you build as well. Okay, so we've got a starting point. Now if I hit the recalculate key, you'll notice the K, which is currently showing a value of 0, will change to 300 because that's the definition there, and the output here will turn out to be, let's see what it turns out to be, 0.6. So the output, if you now right click, you can see the output, and the output there is 18, which is 6% of 300. So Minsky is starting to build all the models for you. So far at the moment, your gross investment is 0, because I haven't defined gross investment yet. Net investment, which is 0 minus 18, is minus 18, so your capital stock will fall. And if you run that model as it stands, it will actually work, but it's going to show you a declining level of capital. Just to indicate that for the heck of it, let's just attach K to one of the outputs, a graph to the output of K, and if I simulate it, this is just a recipe for your capital stock falling down to 0. Okay, but we're going to continue, keep on going, and build a full model. So now that I have capital, I'll just reset back to the value at K0 there. I now want to have this giving me output and also employment. And my output relationship is going to use something that has come out of my work on energy, because what post-Keynesians normally use and what Goodwin used, and we'll use that later when I go straight from definitions, is the idea of a capital output ratio. So if you divide capital by the capital output ratio, you get output, and that's how Goodwin built his overall model. But my work on energy has led me to regard the capital output ratio as the inverse of the efficiency with which machinery turns energy into useful work. Now, since I want that to become how subsequent modelers keep on building dynamic models of the economy rather than the kludgy nonsense that neoclassicals publish, I'm going to actually use that as a multiplier. So rather than talking about capital divided by capital output ratio x is output, I'm going to have capital multiplied by an efficiency term for how efficiently machinery turns energy into useful work, and that will give me my capital instead. So I'm going to have E underscore K, and I'm going to give it a value, say, of 0.3. I'll make it a parameter, but of course in a more realistic model it'd be a variable, and say that this is the efficiency with which machinery turns energy into useful work, and give it a maximum value of 0.45, because one argument, empirically it works out to being about 0.3, 0.4, but it's never going to get much higher than that because of the second law of thermodynamics, and that's something which you can incorporate as a waste factor in a Minsky model once you've got it using this idea of, rather than the idea of the capital output ratio, use the efficiency with which machinery turns energy into useful work. Anyway, that's a bit of a waffle there. So I'll give a step size that I can modify if I need to in terms of making a simulation. So now if I multiply by typing a multiply key, that parameter by capital, I have output. And I'll use the usual symbol of Y for that. From normally economics, it's one of the few terms we seem to have settled on as a standard term in economics is Y for output. Okay, so that's the output side of things. Now, normally what I'd do after this is then divide output by a labor to output ratio. But one thing again which has come out of my work on energy is that I regard the real proportionality is not between output and employment, but between machinery and employment. You have a certain number of workers you need to run a machine. However, you measure how many machines you have, and that is not as much of a problem in post-Keynesian economics as it is in neoclassical, because we're not arguing in post-Keynesian economics that the quantity of capital determines the profit rate. This comes out of a competitive struggle between workers and capitalists over the distribution of income. So the strict measurement of capital is easier, it's less conflictual to talk about an aggregate capital measure in post-Keynesian economics than it is in neoclassical economics. So what I'm going to do, instead of having an output to labour ratio, is have a machinery to output ratio, and I'll call that K colon L, and then subscript R for ratio. But in fact, actually I won't do it quite that way because I want to make it vary over time, so I'll cancel that. I want now another integral reflecting that this thing changes over time. Right click and choose edit there, and I'm going to paste what I just started typing, capital labour ratio. So now I've got another rate of change. So anything you've got with a rate of change is going to have an integral block when you model it in Minsky. So if you go back to the days of the James Watt steam engine, there'd be a large number of people involved in administering it relative to its energy output. That's the important thing to think of here. These days, far fewer workers tending a Elon Musk Falcon 9, again relative to its energy output. And that's the real focus I want to move us away from in modelling production, away from the idea of capital and labour as the only means of production, and bring energy in. So that's one reason I've done all this. Now I've got a capital labour ratio, so I have to have the idea of a capital labour ratio at time 0, and as for what that could be valued at, then I'm just going to give it a value, and there's cheating here and checking so what I've used it in a previous simulation. Just use the value of 1, so 1 worker per machine type story. If you go back to the days when we used shovels to dig, then there'll be 1 worker per shovel, and give it a maximum of 2 in case I want to modify the value, and minimum of 0.1, and a step size of 0.1. This is just to change the initial value. It's not changing the rate of change. That comes in next. So I wire the initial value to the bottom of the integral block, and then I want to take a copy of the KL over here and say that that grows at the rate alpha, and that's the parameter value that Goodwin used for his labour to output ratio. So I'll just use the same, and this is again, in a more complicated model you'd make it a variable, but it's a parameter saying that let's just say that the capital labour ratio grows, and therefore the labour to capital ratio shrinks at 1.5% per annum. Give it a maximum of, say, a 3% rate of shrinkage, and a step size of 1. Again, I don't make much use of these step sizes here, but it's nice to be able to vary a parameter. If you find you've got a wrong value, then you can just press the arrow key as I'm doing now and jump between them. And in fact, I realised that I need to make the step size smaller, so I'll make it 0.001, and now I take it back to what I had initially, which is a 1.5% rate of technical change, as we'd call it today. To me, that is changing the ratio of machinery to labour. So multiply the initial capital capital output ratio by, say, how many machines are there per worker, by the rate of growth of that, wire that up here, and you have another little model. So I'll just actually whack this here and show what's going on. Now this, I don't know why that suddenly happened. That is actually a bug, because when you're on a block, you should be able to draw a wire from the outside of it. There's something about how I've defined that block that means that Minsky is not letting me draw a wire. So I'm actually going to cheat and draw one from over here. That'll still do the same thing. We occasionally have these bugs with integral blocks, and I must have identified hopefully an old bug that we've knocked off in later versions. So run the model and you see that there's a growing ratio of machines to labour. However you work out how many machines you have, that ratio is rising over time. So that's the first step there. So I've now got let's go back to the modelling bit. So here's a capital output ratio. I will just keep a graph there so we can see that when we put the whole model together. I can actually just take a copy of that and paste that next to the graph and just whack it up there. And just to make it more complete, let's put a title up there. So this is machinery to labour ratio. Now this is going to cause another bug in terms of how the display occurs on the graph. It sort of goes outside the bounding box, so we have to go and edit that and make that say machinery mother machinerty. Okay, so that's reasonable. Again, just hit the run button and you see that ratio rising over time. So that's the industrialisation used in more and more mechanisation as time goes on. Okay, and now notice we're actually getting an output level coming out of this. I'll just hit the run and simulate again. And of course that's falling because there's no gross investment taking place. So we're getting the beginning of a model here, but I also want to have employment. And the reason I've done this separately is that normally I said I'd be dividing by output to labour ratio here and then building an overall flowchart. But I want to show you can actually do it from here instead. So I'm going to take a copy of the capital stock and then just hit recalculate and start from the initial level. So if you have capital of 300 and a capital output ratio of 1, then you are going to need 300 workers. So you're going to hire that many workers to produce that level of output. So I'm going to type L for labour here. So number of workers hired. Pardon me. That is also a flow. So now I have something at which I can feed a wage determination element, but to do that I need to have a population level as well. So I need to have the number of people in the society. Again, that's going to be an integral block. Actually, I'll click once more on the integral block and show you another way of doing that in a moment. So I bring this down here, right click and edit it and call this N for population, or number of people. I could use P, but of course P is used for price levels, so N is probably better for number of people. And then simply have N underscore 0 as the number of people initially when the model commences. And let's make that say 600 and just see what happens. I'll give myself a bit of room to change it around if I need to. I forgot to mark that as a parameter, so I'll just go back and edit that. I don't need to do that, it's just makes it neater to see in colour what are your parameters and what are your variables. So now right click and choose copy the item here, and then the parameter that Goodwin used for the rate of population growth he called beta, so I'll do the same. I think he did, so this is at least the parameter that I use, and say that's say a population growth of rate of 2%, maximum say of 4%, minimum 0, step size 0, 1. So now I have beta, which is the rate of growth of population, multiplied by population and integrated and added to the initial value is the level of population. So let's just wire that up. This is the simplest differential equation possible. It's just this is constant population growth. So now if I graph that, we're going to see a rising population. And now if I take a copy of N and put that under here, and then divide L by N, let's just actually, pardon me, not by there, pardon me, I've got the wrong wire. So to get rid of wires, two ways. When you highlight a wire and a blue dot turns up and you don't have anything else selected, then you press the delete key. That just gets rid of what you wanted to. Whoa, now. Okay, here's another, not an error, it's just how sensitive Minsky is. I meant to drag a wire out of K. In fact, I curved the current wire coming out of K. So if I right click and choose straighten, I get rid of that, and now I can drag out a separate wire. And I don't want that to be going straight to L. I want to divide capital by the capital to labour ratio, and that's going to determine labour. So I've finally got that right. Let's hit the recalculate key. So that's saying it's going to be 300 workers. Now that implies if I actually then divide employment by labour, then I get an employment rate of 50%. I tend to use 60% of population as the sort of point at which wages don't change, just as a way to roughly capture what real data shows you. So roughly speaking, in America, when 60% of people have a job, and that includes your children and your grandparents, the wage rate doesn't change all that much. So it's just to get a realistic value for that. So to make that work better, what I can do is just reduce that initial population value, and that will then change what I get there as a ratio. So I now hit recalculate, and I'm going to get a ratio of 3/5, which is 60%. So I'm now to call this lambda \LAMBDA, and that is the way we write the Greek letter lambda in English. And so if I click on OK here and then attach the two, I get an employment rate of 60%, which is going to be my level for no change in wages. In fact, I'll make it slightly larger, so I put the initial value up to 520 and hit recalculate, then I get a value of 57%. So you can see that if you right click you can see the value, and that means that wages are going to be at a level below where wages remain constant, so you're going to get a fall in wages initially in this model, in this simulation. And you can vary that and make a rise if you want to do that instead. That's fine. So let's just now make a bit of space here. I'll just zoom down a bit, because what I want to now have is a Phillips curve relationship. And if anybody who's scoffing about Phillips curves, read Phillips's original paper. It's far richer than the caricature that's done about him in the textbooks. And this is a good starting point. Every model, from Marxist to neoclassical to post-Keynesian, have some idea of bargaining power coming out of the wage level. And this is strictly speaking about bargaining power here rather than the rate of change of prices, as they don't actually have prices in this model as yet, though again it's quite easy to add them to a dynamic model. So what I've got now is the employment rate, and I want to have a parameter which I'm going to call Z for 0, lambda, which is the value of the employment rate that leads to no change in wages. And I'm going to make that, of course, that's a parameter, give it a value of 0.6, enable a range if I want to cheat with it. Again, of course, this would be something you'd work out empirically in a serious model. So now I've got the 0.4 employment minus employment. So I type the minus key first of all, and then press the enter key. That gives me a minus operator. That is now the gap between the actual employment rate and the rate where wages don't change. So to get a linear Phillips curve, which is what Goodwin used in his model, I'm going to define another parameter called S underscore LAMBDA, and that's going to be the slope of the wage change function. Phillips specifically had a nonlinear function, by the way. So if you're going to do a serious model for Phillips, you need a nonlinear function, and it needs to depend on the rate of change of employment and a lagged response to inflation as well. So I now multiply the slope by the gap, then I get the change in wages. And I'll call this delta W, delta subscript lowercase w for wage. Click on OK. So now I've got to bring in the rate of change of wages, and I'll use that to illustrate another way to type the integral block on Minsky. We try to use shorthands that are where the keyboard character looks like the mathematical operator we want to insert. So an integral sign looks like an ampersand, and if you type the ampersand on your keyboard, you'll get an integral block there. I'm now going to right click, edit that, and call this W for a lowercase w for the wage rate, and then I need an initial wage rate. So again, to give myself a bit of choice, I'm going to make this a parameter which can have a value, say, between 0.1 and 1, and whoops, with a step size of say 5%, that should do. Now I feed that into the bottom of the wage rate, so that's the initial wage, and now if I feed take a copy of the wage rate, copy the item, you multiply the actual wage by the rate of change of wages, which is what we've now worked out in here. And then integrate that and add it to the initial wage, you have the wage rate. So actually, let's just type that down here. Now notice that's not connected to L or to lambda. And this is one thing where Minsky differs from standard flowchart programs. Virtually all of them say anything which is an input to any other variable, you have to wire them all together. And what you get is a tangle of wires on the canvas. It makes sense to the person building the model, but becomes indecipherable to somebody who's not building it. So what we do, we don't even need to wire the two together. At some point I'd like to have the idea of a little dotted line to indicate this has got an influence upon the wage rate. But at the moment, the way you read the logic of this model is the rate of change of investment, the rate of change of capital stock as investment, divide that by capital output ratio, you get the employment, get that, divide that by population, you get the employment rate, feed that over here, you get the wage change, multiply the wage change by wage, integrate it, you get the current wage level. Let's just hit the recalculate key. That gives me a wage of 1, of course, that's where I'm starting from. And now I've actually got everything I need to define a model, because if I multiply, if I take a copy of L there, if I multiply the wage by the wage rate, multiply the two together, then I have the total wage bill. I'll use uppercase W for that and call this total wage bill. And wire that together. Now let's hit recalculate and see what numbers we're getting. We've got a wage bill of 30 with output of 90. That's a rather large gap, so I'm just going to increase the initial value to say the wage parameter of 2. Whoops, pardon me, I'm going to hit recalculate rather than, that gives you a profit of 30, which is going to lead in the simple Goodwin model investment of 30, and that's a bit closer to what it'll give you smaller cycles. So output minus wages in the simple model is profit. And to indicate profit, I'll use the \pi, capital P, which gives me the Greek letter capital Pi. And in the simple Goodwin model, what Goodwin presumed was that all profit was invested. So that is the Goodwin model. I hope that's a surprise, because it happens pretty rapidly, and it's much simpler than trying to do the model that Goodwin had. And now what you'll notice is I'm not getting negative numbers anymore. I'm not getting falling output, I'm getting rising outputs. Let's just take have a few more graphs and see what's going on there. And let's label some things here. So this is population. And here we have wage change. So it's another graph. And in fact, I'll make this percent per year and just modify the input, because at the moment it's coming across as a fraction. If I delete that cable and put in a percentage block, then I'm going to get the percentage rate of change of wages. And let's just simulate this for a second and see what happens. And I'm getting wage change going up and down cyclically over time. If I actually want to see more accurately, let's now, because it's an argument of the employment rate, take a copy of employment, paste that down here, attach it to the same coloured input on the bottom, and now let's run it and see what happens. And now we get a linear wage change, and you'll just notice let's just zoom in a bit over here, so I'll just make a bit of a zoom so you can see more clearly. This is one little trick we did to make it easy to see what's going on in Minsky. Notice the dot moving up and down the line. Okay, that's showing you the current value. That's a little trick that I don't think any of the other systems dynamics programs use, just to make it clearer what's going on. And I'll change the option down here to say the bottom is not the year but the employment rate. And I can also make that more obvious that that's clearly a fraction. So if I just delete that wire, then I can feed that through a percentage block. And I can call that lambda percent. I don't need to do that, but it just means that I can use this elsewhere in the model. And then I can attach that to the red line. So now we're graphing the wage change against the employment percentage. And let's also get the wage percentage out of the model as well. So I've taken a copy of Y and W. I'll paste them down here, flip them over. So I want to divide Y by W. So I have a divide by key. And let's take another copy of, just take a copy of that percentage operator and put it through here. And this is now going to be wages share. And the symbol, I don't know what Goodwin actually used, but I use omega, which is the Greek W. And I call it omega percent. And that's subscripted, so, okay, there we go. So now I wire this up and I've got the wages share, and let's just put a graph of these two against each other up here. So if I graph the wages share, let's just flip this around, put a chart in the middle, and now I'm going to model, let's say put wages in green and employment share in, let's go for purple. And this is now going to graph them against time, and I can also graph them against each other. So I'm now going to use a curved line here to go to the, let's go to the blue, and take a copy of that, paste it over here, and also go to the blue. And let's just make that line look a bit neater. So if I drag it out a bit, I can get the dot. You can click anywhere you like on the line and curve it. And now let's just curve it a bit more because it's still getting in the way there. So if I click on a second location, I've got to make sure that I indicate the line and nothing else than the line. So now I've got those two, and I can now fine tune that if I like. So if I drag this dot back a bit, yeah, a bit of mucking around to make things look better. Tyrone Keynes is the expert on doing all that, so check one of Ty's videos to see how to do it rather better than I'm doing it. But now let's just hit the simulate button and see what happens. And there's your cyclical growth model. So it's fairly easy to build a model in Minsky, and I hope it's fairly easy to understand what's actually going on here. And that is, of course, a flowchart model, in that I haven't derived logical values for the employment rate and the wages share of GDP, but those are the two dominant ratios in this particular model. So I'm going to do that next after I take a bit of a break. Right, so that's building a Minsky model, or the Goodwin model in Minsky straight from the flowchart. But what I want to illustrate is why I regard Goodwin's model as so important, because it's possible to derive it directly from macroeconomic definitions. And one of the reasons neoclassicals A have stuffed up the economic theory, but B refuse to consider other approaches is they think you must build macroeconomics from good foundations, and the word they insert between good and foundations is microeconomic. Now, that's wrong. You can't build a model of an emergent system from its components, directly from its components. That's the mistake they make. They extrapolate from micro to macro. The extrapolation fails because of the impact of aggregation. But it's possible to work in the opposite direction and say, well, let's actually found macroeconomics on macroeconomic definitions. So I'm going to define the employment rate, as I did in that model, as the number of people with a job, L, divided by population, N, and the wages share of GDP, omega, as wages divided by GDP. And apply some simple rules of calculus here to percentage rates of change. And this makes it much easier to derive a model, not just for people who are experts, but also for people who don't have any real knowledge of mathematics, because there's a simple set of rules. If you have two variables multiplied together and you want to look at their rate of change in percentage terms, then the rate of change of the product is the sum of the rates of change of the individual elements. And if you have a ratio, so you've got a rate of, you've got a and B, where A and B are both variables in a system, then the percentage rate of the rate of change of the percentage of the ratio is the same as the gap between A on the numerator and B on the denominator. So a simple rule is to apply through here. And if you look at wages share of GDP, then the percentage rate of change of the wages share of GDP is the percentage rate of change of the wage bill minus the percentage rate of change of GDP. And that simply says the wages share of output will rise if the total wages grow faster than GDP. Now that's a fact. And that's why I'm using the definition term here, the 3 dash equals sign rather than the 2 dash equals sign, because this is actually simply definitionally true. It's not something you can dispute without disputing the definitions, and then you're in a quagmire territory. And the employment rate, which is L divided by N, means the percentage rate of change of the employment rate will be the percentage rate of employment minus the percentage rate of population, and that therefore says the employment rate will rise if the rate of growth of the workforce exceeds the rate of growth of population. Well, that's again simply a true statement. So what we've done, we've gone from a set of incontrovertible definitions to those same definitions stated in dynamic form, and therefore we can build a model. So we actually do this, we start from those two, apply those rules, and I'm repeating myself, or I didn't check. Oh dear, I've got it twice. Pardon me, hang on, ignore that please. So now, what I'm now just spelling it out in more detail, and let's now combine that with other definitions. So again, I'm not doing the extra step I showed in the building the flowchart model of talking about a capital to output. I'll stick with the output to employment ratio, which I think Goodwin used the term A for, and I do as well. And then V for the capital to output ratio. Now, that's what I've replaced with the efficiency of capital, but it's just easier to derive it this way here. And to convert this into differential equations. So 1 over lambda d lambda dt, which is lambda hat, which is again lambda hat over L divided by N, and omega the same way. And I'm going to now make a range of assumptions. So I'm going to assume there's a uniform real wage, so little w, as I used in the model, is there. I'm ignoring the issue of capacity utilization. That can be brought in a more complicated model. I'm going to have a constant ratio of capital to output, and that's one reason you use a capital output ratio rather than what I've done with labour. Exogenous population growth and exogenous growth of the output to labour ratio, all of which I included in the previous model. So I've got no change in the capital output ratio. The wage bill is wages times the level of employment. The rate of change of the labour to output ratio is alpha. The rate of change of the population is nu. So I've just used nu there rather than beta. So deriving it, and brace yourself, there's going to be a lot of equations turning up running left to right on the screen. So let's unpack that. So you first of all use the rule that I've shown. So you've now got hat L minus hat lambda, which is 1 over lambda d lambda dt, is equal to hat L minus hat N. And L is you can substitute the output to labour, the labour to output ratio in there, and then expand that out using the same rules. So you finally find that the rate of change of the employment rate is the growth rate minus population growth minus technical change, effectively the change in the output to labour ratio minus population growth. Do the same thing for omega, slightly lengthier. and a cancellation occurs, which is rather nice as well. So the rate of change of wages share is rate of change of wages minus rate of change of GDP. You now get W times L inside here. That's the simplification I did earlier. So you now multiply those two out. Now you've got rate of change of wages share is the rate of change of wages plus the rate of change of employment minus the rate of change of output. Now for L, you make the same substitution I did up here. L is Y divided by A. You can then expand out, that is now going to be rate of change of wages plus population growth, plus GDP growth, minus rate of growth of the labour output ratio, minus output. Well, these two cancel, and you get a very simple outcome that the rate of change of the wages share is equal to the rate of change of wages minus rate of change of the labour to output ratio, or output to labour ratio. So I've just now got to define what the only things I don't have a strict definition for yet in this equation are Y itself and the wage rate change. So let's just go through Y. Pardon me, I did it too quickly. So again, in this simple model, I've got the rate of change of output is the rate of change of K divided by V. That's the rate of change of K divided by the rate of change of, minus the rate of change of V. We've assumed that's constant, so the rate of change of output is identical to the rate of change of capital in this simple model. Now, Goodwin also made the assumption, and I used that in building the model beforehand, that gross investment equals output minus wages. And I include depreciation, which Goodwin omitted, and that was a mistake. It's easily corrected. So now when I go through the overall logic here, reading line by line, I've got the rate of change of capital is a gross investment minus depreciation. Substitute profit for gross investment. We've still got capital inside there. I'm now expanding out what this is. So I'm now saying, I've actually divided through by K here. So I've got 1 over K decayed here. So I've got in terms of K hat is now profit divided by capital minus depreciation. Profit divided by capital is output minus wages divided by the capital output ratio times Y minus depreciation. You get divide through by here, you get 1. Divide here through by here, you get omega. So 1 minus omega over the capital output ratio minus depreciation is the rate of change of capital, and that's also the rate of change of output. So I've now got a full expression for the employment rate, the rate of change of the employment rate, and that's the percentage rate of change of employment is 1 minus the wages share divided by the capital output ratio minus the sum of the rate of growth of technical progress, let's say, plus population growth plus depreciation. Now that just leaves wage rate to define, and I've already done that in the previous model. I've said the wage rate is determined by a linear Phillips curve. So the final model is there. And in differential equation form, I've got to multiply through by omega and lambda because of omega hat is 1 over omega, the omega dt, and lambda hat the same thing. So that is now expressing Goodwin's model as a set of differential equations. And that, even though I know it's complicated when you first see it, that is a lot easier. Let's go back and take a look at Goodwin's paper. It's a much easier derivation to follow than what Goodwin is doing here. Goodwin is still brilliant work, and he was the guy who originated the model, so it's no criticism to say you can do it more simply. But if I simulated that in Minsky, I'll just bring up the Minsky model here. And that's the model defined across. I'll just make it full screen. So that's exactly what I've explained a moment ago, step by step, and you get the same cyclical behavior that you saw in the other model. Now, the beauty of doing it this way is that this is saying Goodwin's model is derived from strictly true mathematical definitions with incredibly simple simplifying assumptions, constant wage rate, linear reaction of workers to the level of employment in terms of setting wages. That's all pretty fundamentally it is. And therefore I see Goodwin's model is the alternative to what the neoclassicals use, which is Ramsey's growth model from 1928, with all the usual neoclassical utility maximizing and accurate capacity to predict the future as being rational behavior. All that stuff is gone. And Goodwin's model unfortunately suffered a bit of a status kick with a paper by Harvey in 2000, and Harvey had made a simple transcription error in going from his PhD thesis to the final conclusions. He was using percentages, and he forgot to convert to fractions, and got the result therefore that the equilibrium, which you can calculate for the Goodwin model fairly easily, was way outside the data, and therefore he blamed Goodwin, was simply an error in how he transcribed his own PhD thesis, which he's rather apologetic about. We had a hard time getting this correction put into the literature, but Grazelli and Maheshwari managed to do that in 2014, and they pointed out the key reporting mistake that Harvey made in his empirical criticism of Goodwin was that the quantities in the top 5 rows of his table were all off by a factor of 100. I have to say, some guilt of mine here. I reviewed that paper, and even though I was upset about the conclusion that Harvey reached, that Goodwin's model didn't at all fit the data, I still agreed it looked okay. I was looking at a table of numbers, all the usual numerical stuff you see for an econometric study, standard deviations, chi-squareds, etc. And I didn't like the look of it, but we were stuck with it. Then I thought, well, I'm going to continue using Goodwin anyway. So some years later, I thought I'll build a graph of the Phillips curve from Harvey's model, and then I graphed it, and it just was off the numbers, which is crazy for this Phillips curve. So I wrote to him, and then that's when he told me he made what he called a simple schoolboy error, which is correct. So what Grazelli and Harashi did is then use the strict simple Goodwin model I've just shown and fitted that to European OECD data, and found that it fitted the data quite nicely. Now, I know this is a pretty fast introduction, and I'd never recommend trying to read Goodwin's paper to work out what's going on in the model, but it was quite complicated to read. So I highly recommend John Blatt's book, Dynamic Economic Systems. One thing I potentially can take some credit for over time is that this book was out of print for decades. And then I think because I think I played a major role here, because I hammer how good the book is, the publishers finally re-released it, first of all electronically and now in paperback, so you can get a copy of this brilliant book again and get a much better explanation of Goodwin than I've given here, and then certainly than Goodwin himself gave. And the next lecture I'm going to go into why the neoclassical model, which uses not a Leontief expression where the Leontief equation says output is some constant multiplied by capital, which is what I used in both these models. Let's go back to, hang on, where have I got the one I've just built? This one. So my production ratio here says output is a constant times capital. The neoclassicals make that variable and think they're more sophisticated. In fact, the variable they use is an unintended nonlinear remapping of a simple adding up of output is equal to profit plus wages. And it's neat and plausible, and like so much of neoclassical theory, wrong as well. That's the next lecture.